Hi everyone, this is lecture video 8, and with this lecture we are starting a new chapter. It is chapter 3, and throughout this chapter we will be talking about differentiation. And the topic of this video is the section 3.1 titled Tangents and Derivatives at a Point. So, as you remember, we talked about these secant lines, and we say that if you approach this point Q, here, this is our point Q, if you approach this point Q to the point P on your curve, then all those secant lines, what happens to all those secant lines? They will be approaching to this tangent line, right? So we will use this idea again here to define the tangent line and the slope of it. Okay, let's use that idea again. Let me draw better. So what I am doing right now is approaching this point Q on the curve towards this point P here. So all those secant lines, these are all secant lines, you know. Secant lines means a line connecting 2 points on your curve, okay? So these are all secant lines. And as the point Q moves on the curve towards the point P, just like here, for example, at the first step, the point Q is here, next it is here, next it will be here, here. So following this direction on your curve towards P, as Q goes to point P, then what happens to these secant lines? We see that when this happens, then all the secant lines, maybe I can write it here, all the secant lines on your curve goes towards this particular line, which is a spatial one, and it is called as the tangent line. When Q touches this point P on your curve, then this secant lines becomes this one, which is the tangent line to your curve. Okay, so all those secant lines approach to tangent line. Okay, and let's look at the xy components of the given points. Here, this point is x0, then the image of it here will be f of x0, obviously, and here we call this point as x0 plus h, that's why this is the image of it. And you see that this length is exactly h. So as Q moves towards P on your curve, what happens to h? As you can see, at every step, you get a smaller h, smaller, so that h goes to 0 when Q goes to point P. Okay, so as h goes to 0, all the secant lines approaching towards this particular pink line, which is the tangent line. Now let's talk about the slope of the secant line. Slope of secant line. What is it? We can easily look at this length here and this length here. We can measure the length of this size of this little right triangle here, because slope is what? Slope of this black secant line is the tangent of this angle, you know? Tangent means opposite edge divided by the adjacent edge. That's why now you can tell me the formula here. It is the ratio of this difference. So if you want to measure this length here, which corresponds to this part, it is obviously the difference of these 2 points given by this expression, right? Let's write that down here. It is fx0 plus h minus fx0, and what we have at the denominator. So this should be at the denominator, it is just h, as you can see, so divided by h. This ratio gives us the slope of the secant line. Then let's try to relate this to the slope of the tangent line, okay? So here we have tangent line. In fact, we did this in one of our previous videos. So now we want to talk about the slope of tangent line. So to relate the slope of secant line to the slope of tangent line, what you should do, we already say here that said here that if you let h goes to 0, then your second line becomes the tangent line. That's why all you need to do is to put a limit at h goes to 0 thing in front of this ratio, in front of this quotient, right? So if you put limit operation in both sides, maybe I can, okay. I can express it like this. Let's take limit of both sides as h goes to 0. Limit as h goes to 0. So limit of slope of the second line. Second line as h goes to 0 is the same as, you know, we already derived this ratio for the slope of the second line. All we are doing now is to putting this h goes to 0 thing. So you know what happens if you take the limit of all the slopes of second lines as h goes to 0. So then they become the slope of tangent line, right? So that's why we have this particular equality for the slope of the tangent line to our curve y equals f of x, at which point this pink tangent line is drawn at this particular point here, okay, at x equals x0. So this is the expression that we will be using for what? For the slope of the tangent line, okay? Additionally, you just put limit h goes to 0 in front of the expression that we find for the slope of the second line, okay? So that's the relation. And I can now relate the slope of the second line and the slope of the tangent line if you put here limit h goes to 0 thing. So this is what is written here for the formal definition of the slope of the tangent line, okay? It comes, this expression obtained by considering the slope of the second line, and then you consider, I mean, you just take the limit of it as h goes to 0. H goes to 0 here means you are moving this point Q on your curve towards the point P, okay? I think everything is clear so far, right? So now I can call this expression as M. M is the limit of the tangent line thing. So it is a notation for it. Okay, so if your curve is y equals f of x, and if this point, which is on your curve, x0 point here, you want to draw a slope, you want to find the slope of the tangent line drawn to your curve at particularly this point, then this is the expression giving it. So then let's apply all those things in this example. You see, this is our function now. This is our y equals f of x curve. And we want to prove that at any point A, which is different than 0, the slope is given by this expression. So we can prove it by using this limit, by computing this limit here. So here you see this pink line, red line, right? What is that? It is the tangent line to y equals f of x curve. In this case, f of x is given as what? As 1 over x. And we are drawing this tangent at this particular point A. So let's talk about the slope of it, okay? So its slope of tangent line is denoted by M, and it is given by this limit operation here. We will be applying this limit here. So x0 plus h, fx0 divided by h, right? Let's try to evaluate these things because we already know the expression for the particular function. H goes to 0. So f is 1 over x. F of x is 1 over x. So you are evaluating 1 over x function at this particular point. That's why I need to write like that. Right? Okay, then minus this is 1 over x0 divided by h. By the way, here the point x0 is given as a in this particular example. Let's put a instead of x0 because it is given as a. Just a matter of notation, you know, instead of x0, we choose any point different than 0, which is denoted by a here. Over a. So this is the expression. Then keep computing things. This is what, if you take the difference of these two rational expressions, you will obtain a minus, take the difference of denominators minus h. What you have at the denominator now, you have this common denominator. It is a times a plus h times 1 more h here. Now you start simplifying things. After you simplify a's, then you are allowed to simplify h's there. This means that the result for your limit is, okay, let's try to see. What do we have at denominator? Just minus 1. What we have at the denominator? A times a plus h. We are assigning h to 0. So what is the result then? This part goes to 0. So the result is minus 1 over a squared. So at any point a different than 0, the slope of this tangent line is given by this expression, which is computed by this limit definition. Okay. Next, what we can do. Okay, this is the slope at any point drawn to your curve. Here, we assumed already that a is different than 0, so this is a defined expression. So now we want to find the slope at this point, the slope of the curve at the point where a equals minus 1, okay? Now we are looking particularly at this point where a equals minus 1. We already know the expression for the slope. It is minus 1 over a squared, so minus 1 over minus 1 squared, because a is chosen to be minus 1. So the result is just minus 1. And now we can, as it is indicated here, the slope is minus 1. And now we can try to find one more thing. So here, another point is given. This point is minus 2. And let's try to write the equation of this tangent line, okay? Maybe we can try it in the positive part, like this point is 2. The slope is minus 1 over 4. Why it is like that? Because the slope is computed from this expression. It is minus 1 over 2 squared, so minus 1 over 4. And now I want to write the equation of this tangent line. Equation of tangent line to our curve drawn at the point x equals 2. How do we write tangent line or line equations? There are two things that you need to know: a point on the line and the slope of it. So we already have all those informations, right? So y minus, what is the y0 component of your point? You see it is here. And this is the x0 component. That's why y minus 1/2 is slope minus 1 over 4. We already find it here. Then x minus x0 point is 2. So this expression gives you the equation of the tangent line drawn to your curve at this particular point, okay? Okay, I hope everything is clear with this example. Now look at this definition. This definition gives the general version of the previous one. Okay, the derivative of a function f at a point x0 is denoted like this. In fact, it is nearly the same. At the right-hand part is the same, which is the slope of the tangent line. Now we are relating this slope to the first derivative of the given function. So what we are defining here is the derivative of a function at a point x0. So the notation, we will be using this notation for the derivative of the given function at some particular point x0. What is the notation for it? Here it is. It is introduced for the first time here. So the result of this limit, we already know that it is the slope of the tangent line. Now, from now on, we will take the result of this limit, which is the slope, as the first derivative of the given function, okay? So this will be the first derivative of the given function, and it is the same. You see, I'm repeating and repeating overall again. So this is also the slope of the tangent line to our function at which point? At x equals x0. Okay, so we defined at this point, what does it mean, the derivative of a function at a point? It is this result of this limit. If it exists, it will be a real line. So the first derivative of your function at the given point will be a real number. And geometrically, it has a meaning. The first derivative has a meaning, geometric meaning. What is it? It is the slope of the tangent line. Okay, so let's move on. And what is explained here, this is kind of the reminding. Okay, I already explained this second line business. So if you keep moving this point towards the point P on your curve, okay, here, Q is here, then you start moving Q towards P like this. At each step, you draw a new second line like this, and then you see that the points, as the points Q approached P, all the second lines are approaching. As Q goes to P, this means that as H goes to 0, what happens? Second lines are approaching towards the tangent line. And here is another figure describing that. You see, if you move all those second lines and your point Q towards the point P, second lines approaching to tangent, when as H goes to 0, this means that Q goes to P, okay? And you can do this also on the other direction like this. And let me also put here one more time, what is the slope of this tangent line? Slope of tangent line is denoted by M, and it is this limit, f x0 plus h minus x0 divided by h as h goes to 0. And without the limit, just this part is what? It is the slope of the second line. And if you send h to 0, meaning that you are sending the point Q to the point P, this expression becomes the slope of tangent line. And at the same time, what we have, at the same time, this is defined as the first derivative of your function, right? Okay, so here is the summary about what we have done so far. So this expression, our famous expression, gives us what? This is the slope of the graph at the given point. It is also the slope of the tangent line at the given point. First and second sentence are basically the same thing. At the same time, remember from our previous lecture videos, this is the rate of change of f with respect to x at this particular point. In fact, it is instantaneous rate of change, right? And finally, we related the slope of the tangent line with the first derivative, and we take this slope expression as the first derivative of your function. So we define the first derivative as the slope of the tangent line, okay? So this expression gives you all those things. They are all the same, okay? So let me show you just one example, then I will stop for this video. What does it say? Find the slope of the functions at the given point, then find the equation of the tangent line to the graph there. So we can do this for 11th one, for example. We want to find the slope, denoted by m. This is the slope of the tangent line, at which point we want to find it at x equals 2. So, okay, this is also related to the first derivative of your function. Remember, this expression is the same as the first derivative at the given point. So now I pass to the limit part. Limit of our function 2 plus h. You see, instead of x0, now I am putting 2, f2 divided by h, okay. Limit h goes to 0, what is f2 plus h? You know this expression for your f. So take the square of your point plus 1. And similarly minus what? Square of 2 plus 1 divided by h. Okay, what do we have done? This is limit as h goes to 0. What we have here is 4h plus h squared plus 1. This is minus 5. Okay, 4 plus 1 is 5. It is simplified with this one, divided by h. So we are really close to the result now. So take h parentheses, 4 plus h divided by h. You see you have a very nice simplification again, showing you that the result is you are sending h to 0 after you simplify. This goes to 0, right? So the result is 4, which means the slope is 4. We also want to write the equation of the tangent line. So let's write that. Equation of tangent line to our curve to f of x at x equals 2. How do we write it? You know, y minus y0, m times x minus x0. This is the general structure of the equation of the tangent line. So what is the y0 component of the given point? Our point is 2, 5. So this is x0 point, this is y0 point. Okay, so y0 is 5, x0 is 2. What is the slope? And the slope is computed as 4. Let's insert all those information. Y minus 5, x minus 2, and we solve the slope as 4, which completes the equation for the tangent line. Okay, so I stop here. See you in the next lecture video.